Okay, very good morning. Now, yesterday we went through a session where I showed you how you can systematically develop a time series model by following certain procedure, and towards the end there was a question from one of the students after the end of the class as to what this AIC that we had used, Akaike Information Criterion, is actually quantifying. So, just for the benefit of everyone, although we will not discuss in detail, I just want to mention that this AIC is actually a function of the number of parameters P and the model also, right. So, it is a function of both your P and the model M, and there is a mathematical expression here for computing AIC, depends on how you look at it. For example, one of the expressions that is originally given by Akaike involves the likelihood function, which we have not discussed yet, but we will soon do so. So, the first term is log likelihood. If you do not understand what is log likelihood, then you can think of this being replaced with n log sigma square, or you can say okay. So, let me put it this way, sigma square E hat. All right. The sigma square E hat is the estimate of the noise variance that you get, plus another function, another term which contains a number of parameters in the model. Rather than worrying about exactly the exactness of the expressions given there, it is important to interpret each of these terms. The first term signifies the fit that the model has achieved, that is the goodness of fit. If the model has fit the data very well, the sigma square E, although we say here sigma square E hat, truly what happens is that it is nothing but the sum square prediction error, averaged sum square prediction error. So, 1 over n sum square error over the data points that you have fit. When I say error, here is prediction error. So, as I increase the model order for a given type of model, the first term actually goes down, but then you are increasing the second term because you are increasing the number of parameters in your model. And what does the second term signify? As we will learn later on, it signifies the amount of error that you are incurring in the parameter estimates. Typically, as the number of parameters that you include in your model increases, the error in the parameter estimates will also increase. So, the second term is a quantification of that, and now you can see there is a trade off between this term and the second term here. As you increase the model order, the first term lowers, but the second term starts to shoot up, and you are looking for that point, that trough. If you were to plot AIC versus P, that is the number of parameters. Ideally, Akaike expects to see this kind of a point there, and we are seeking this point because this is the kind of optimal trade off that you have achieved. If I have a model with very few parameters or kind of no parameters, then the first term is going to be very high because you have not fit anything, or you have not done a proper job of fitting the data. But as you walk on this axis, walk down, you are increasing the number of parameters, thereby having more and more parameter power to explain the data. Therefore, the first term starts to decrease, and at some point the decrease in the first term becomes marginal. That means, let us say in the yesterday's example, we fit a 5th order AR, we could have gone to a 6th order AR and achieved a lower prediction error, but then the improvement that you get in that respect is going to be insignificant compared to the shoot up in the errors that you are going to see as you move from the 5th to 6th order. So, that is the trade off that you are increasing. So, the extreme cases where you have large number of parameters in the model, heavily over parameterized model, which does a very good job of fitting the data, but what happens is the error in the parameter estimates is so high, as a result the AIC starts to shoot up, it takes a U-turn. So, you are looking for this point of U-turn And this is all idealism. In practice you may not see such a sharp turning point, you would rather see a flat region, kind of semi flat region, and then you have to pick based on parsimony and so on. So, that is the principle behind AIC, but we will talk more about it later on, and this likelihood function will become clear once we discuss the concept of maximum likelihood itself. So, let us get back to the discussion, and there is one more point that I want to say, that we have used certain tools yesterday in building the model, and as I said, there are some minor issues with using these tools which can go unnoticed by an ordinary user. So, I would strongly recommend that you visit Stauffer's website, where he explicitly talks about these issues concerning the use of ACF, PACF, and even the TS diag that we had used, that routine, and a few other routines that you would use in future. So, it is important to be aware of those issues, and Stauffer has some remedies in terms of a new routine and so on, but please go through that page. You just go to Stauffer's website and look for issues with R, and of course, he has some very nice satire and sarcasm there. It is really fun to read the way he brings up the issues and so on. One of the things that he also points out, as we know, when you load new packages in R, there are going to be routines whose names overlap with those in the existing packages, and therefore, when you load a package, it says these are being masked and so on, and his take on that is one day R will actually get into an infinite loop, where there will be some routine which will mask, and then again another routine which will mask, and it gets into infinite loop, and that is how R will end its life or something like that, but anyway. So, anyway, there is another package that I am going to talk about today, which is very useful and you should install it, but let us start our theory session, and then in the course of the lecture, when I demonstrate how to fit for example trends, or how to identify seasonalities and so on, at that time I will talk about the package. So, let us get started with the theory part again. Until now we have assumed stationarity, but as we have discussed before, many processes do exhibit non-stationarities, and that is the topic of today's lecture, and there are different types of non-stationarities, just like there are different kinds of non-linearities. So, you can have mean non-stationarity, you can have variance non-stationarity, and within mean non-stationarity you can have two different types, deterministic one and stochastic one. And then to top all of this, you can have periodicities, or in general seasonality. Seasonality is a generalization of the concept of periodicity. So, what we will do is we will actually start with the mean type non-stationarity and discuss the deterministic ones first. So, let us do that. When you look at the deterministic trends, typically you are looking at polynomial functions of time, whereas when you are looking at stochastic trends, you are looking at typically a random walk type of effect, and we have talked about this before. Now, what we shall do is primarily focus on integrating type effects, but I will also talk about how to get rid of trends. There are many series which exhibit trends, and there are other ways of handling deterministic trends which I am going to briefly talk about, but the focus is going to be on integrating type non-stationarities. In other words, we will mostly look at ARIMA models, and the advantage with working with this ARIMA models is that to a certain extent they can also handle trend type non-stationarities, although it is not recommended to use that, and I am going to talk about certain subtle aspects of working with ARIMA models. So, let us move on, and before we do that, also sorry, there is another point that I want to make. When we talk of deterministic effects, there are again two types. One, as we have already noted down, polynomial functions of time. Those are the kinds of trends, we have seen this before. Then you can have another kind of deterministic effects which are due to exogenous effects, that is some external variable is introducing these kind of deterministic effects, and in such cases you will have the knowledge of the external variable, and therefore you will fit you will include that or factor that in your model as well. So, in other words, no longer do you consider V as purely a function of time or its past, but also now as a function of this external variable. And that is essentially the subject of system identification. That is how time series community views system identification as. It says that whatever inputs you know are causing change, producing changes in the response variable that you have can also be factored in. And for example, in the ARIMA routine that we used yesterday, there is an option to include exogenous variables as well. And when you do that, what the models that are born are called ARIMAX models, the X standing for exogenous. And that is why a lot of nomenclature in system identification also is born from the time series literature. So, you have ARX models, for example, in system identification, ARX models. It is an AR model with exogenous effects, or you have RMAX models which is an ARMA model for the noise part, and then an exogenous effect being included in the model. The exogenous effect is also typically considered as being modeled as an LTI system, that is the input or the external variable that you have is assumed to be affecting your response through an LTI system, and that is the subject of at least linear system identification, but we will not go through that. Nevertheless, if you are given exogenous variables, you can still use that information and factor it in your ARIMA routine and your ARIMA modeling essentially. So, let us come back now and talk about time trends that are purely function of time. We do not worry about exogenous variables now, and there are two approaches to handling trends. One is of course fitting a polynomial to the given series and then working with the residual. The other approach is eliminating the trend by the use of a suitable filter, and we will talk, we will discuss both these approaches now. So, for example, let us say there is a linear trend, right. Vk is some alpha naught plus alpha 1 k plus some wk, and wk can be modeled as an ARMA process, stationary invertible ARMA process, and we can assume it to be 0 mean without loss of generality. So, the procedure here or the practice here is to fit a linear model in time to this series that is given to you and then work with the residuals. How do you fit this alpha naught plus alpha 1 k? Using standard least squares methods. Of course, there are subtleties, because when you are using least squares methods, the optimality, the efficiency and the consistency of least squares methods depends a lot on the nature of wk, but we ignore all of that. We will assume that you will get optimal and efficient estimates and so on. Typically, they are not so violated, at least in this case, so much, and just fit a linear regression kind of model, and that is achieved by LM. In R, I have already shown you a routine called LM, which does the linear regression for you, and there is a better routine that I will talk about very soon in another package, which will make your life a bit easier in terms of fitting these trends. So, what do you do? Once you fit a straight line here, then you work with the residuals. How do I know it is a linear fit? Right? It could be a how do I know it is a linear trend? It could be a quadratic trend, it could be some other polynomial trend. Yeah, you will have to make a visual inspection guess and then re-look at the residuals. If you still find a trend, then go back and make corrections to your polynomial trend and so on, until you feel that there is the series is stationary. There are tests again for this, which will tell you whether the underlying the series has a linear trend or not and so on. We do not go through such tests here, but you are most welcome to look up the literature. Now, alternatively, as I said, you can use the filtering approach. In R, I will demonstrate how to do the former one, which is the fitting the trend shortly, but let us quickly discuss the second approach as well. So, if you look at the second approach, I have beta naught and beta 1, that should be actually alpha naught and alpha 1. So, just I will make that correction later on. So, when you look at the expectation of Vk, you can see that it is simply alpha naught plus alpha 1 k. Now, that means the in some sense the deterministic component is the average of the given process, correct. This is the basic idea in using the filtering approach. What is done in practice is you take sample mean of the series, but not of the full series because your mean is changing with time. You take a window of data and compute the sample mean, and of course, that window length is a user defined parameter. So, you take local averages and generate these alpha naught plus alpha 1 k. In this kind of an approach, we do not fit or we do not estimate alpha naught or alpha 1. I just want this component, right. So, if you go back to the notation that we have used, I just want this m k, that is all. I have V k being expressed as m k plus w k. In the first approach, we have assumed a parametric model for m k, and then we obtain estimates of alpha naught and alpha 1 or accordingly whatever polynomial we assumed. In the second approach, we note that expectation of V k, that is the average of V at any instant, is m k itself because we have assumed w k to be 0 mean, which means of course I cannot work with a single point, therefore I will work with a small window of the given series and locally estimate m k. So, what you are doing is you are not exactly estimating m at each instant in time, but you are assuming you assume that it is locally invariant, the mean is locally invariant. That is an assumption that we are making, which obviously is not correct, but that is one solution in practice. So, I just what I do is I construct a weighted average or a simple average of the series over a window of data, keep moving along and then keep estimating the trend. That is the idea. Now, this averaging business amounts to filtering. I do not know how many of you are familiar with filtering. Filtering, the very name itself suggests that we are eliminating some components of the series. From a frequency domain viewpoint, filtering amounts to only retaining certain frequency components of the series. When it comes to averaging, as you will realize later on, averaging is nothing but a low pass filtering kind of operation. That is, we allow the low frequencies to be retained while the high frequency stuff, the rapidly changing fluctuations are smoothened out, they are flattened. Right, naturally when I take average of any signal that has very rapid fluctuations, the net result is a smooth signal which is devoid of those fluctuations, and those rapid fluctuations belong to high frequency domain regime because they are changing very frequently. Very simple, it is just common sense. So, any averaging operation from a filtering viewpoint is equivalent to letting the signal pass through a low pass filter. Low pass filter is one filter which allows only low frequencies to go through, and that is why this approach that we have, where we locally average the series and estimate m k, can be thought of as a filtering approach. And based on this, there are several ideas. This is the one of the ideas here, where you use a two-sided moving average filter. So, you are standing at, let us say, at some point into the series in the initial point, depending on the length of the filter you have to position yourself. You can start from observation 1, but then you would not have the left hand side of the data. So, your series will look like this. For example, if there is a linear trend and then maybe there are some oscillations and then on top of it you have these irregularities. As we have discussed, the classical approach is to think of the series as being made up of trend plus seasonal plus an irregular component, and the modern approach is to actually look at it using a multiplicative kind of model. We are looking at the first approach. So, if you have a linear trend like this, what you would do is, using this idea, you would construct local averages. So, you take this window of data and then construct an average, and then you move on, you march along in time. When you are standing here, if you are using a two-sided filter, that means at every instant you position yourself and look to the left and right and construct an average, right. In the initial points and at the final points, you will have border effects. That is standard with any filtering approach, you will run into that issues. We also have border issues, right. Even any country will have issues at borders also. Anything will have issues at the borders. When you are coming in the last minute, then there is a border. When you are submitting an assignment at the last minute, you have a border issue. So, likewise in filtering also at the ends, these are called end effects or border effects. Invariably you will experience those effects. So, at these points there are some solutions, but as you move into the series, the border effects vanish. And what is being suggested, for example, as I have shown on the screen, is to use a simple average, weighted average, simple average, but you have equal weights 1 over 2m plus 1, where 2m plus 1 is the length of the filter. How do I choose m? Yeah, that you have to play around with. Unfortunately, in this kind of an approach, which is a non-parametric approach, because you are not force fitting any polynomial onto the trend. That is why it is called a non-parametric approach, whereas the previous one force fits a polynomial, and that is why it is called a parametric approach. And you can see there are advantages to both. In the non-parametric, you are not presupposing any polynomial for the trend, but then you have to choose the length of the filter, which is okay. You do play around with it, there are some recommendations and so on. And of course, a simple average may not do a great job, because you may want to give more importance to points close to the point that you are located standing at. Suppose you are standing at this point and estimating m, you want to probably give more importance to the points within the vicinity and less importance to the points far off from where you are positioned. A weighted average is definitely better, and that is the idea. For example, in the Spencer's method, it is not the Spencer that we have outside in Velachery. This is a 15 point moving average filter, that means m is 7 here, and the weights are given by Spencer. But by any means, you should not think that this is only filter. There are several other recommendations available for this, but what you should remember this as a filtering, one as a filtering approach, two as a non-parametric approach, in contrast to the first approach where we fit a trend. Which one should I choose? Well, it depends. Sometimes you may have to play around, but sometimes if you see that there is a trend, it is better. Parametric approach in general is always good when you have the conviction that yes, that model is correct. A non-parametric approach is good to begin with when you do not have any prior information, you do not know what it is. For example, you can use this non-parametric approach to estimate m and then examine m separately, how m looks like. You may not be able to see that trend when it is clubbed within the series with the other components of the series. Once you have estimated m, you can take a relook at m and then hypothesize a certain function of time, and then go back and fit a parametric model. This is a standard thing that is followed in any modeling exercise. First you begin with a non-parametric, if you do not have any prior knowledge, get some insights and then use a parametric approach. Okay.